Hello, thank you for the introduction. And my name is Sergio, and today I'm presenting and talking a little bit about some of the work we do in the Oncology Research Department at Lunit. But first, let me start with our mission, which is conquer cancer through AI. Conquer cancer through AI. And to do this, we pursue two main pillars. One is the early stage cancer detection. From images from radiology like X-ray or CT. And we do this because research shows that the earlier we detect cancer, the higher are the chances of survival of these patients. And the second pillar is treatment planning, because each cancer is different and each person is also different. So the treatment that works for someone may not work for someone else, and we need to plan the best treatment for these people. And this is a combination of two modalities: pathology, that deals with microscopy images, and oncology, that predict cancer treatment. And by these pillars, we want to achieve our goal, our objective of improving the survival of cancer patients. But for today, I will focus on pathology, where we use most of computer vision in the oncology research department. So, histopathology in cancer is the study and analysis of microscopy images. To make a bridge with computer vision tasks, these doctors, these pathologists, they do detection and classification of cells, and they also do semantic segmentation of tissues. So basically what they are trying to do is to understand the relationships that live underlying the cancer, the relationships between cells and tissues. But this is subjective and time-consuming. It's subjective because these experts, they disagree a lot between them. And it's time-demanding because just check how many cells exist here. And these images are huge, which leads us to the first challenge that I want to introduce today. These images are really large. It's really large-scale image. So these kind of images, they are commonly 100,000 by 100,000 pixels in size. And this is just a common size. They can be larger than this. Just look at this. We start from this image on the left, and we can zoom in until the cell level. To give a better idea, let's imagine that instead of cells and tissues, we want to detect cars and segment roads and buildings. And by the way, this is right outside of COEX. But we don't do just here. Not even here. We detect all cars and segment all roads and buildings in all this area. So this is a huge task, and it's really large. This is challenge number one. Challenge number two is, since we deal with these low-level image tasks like segmentation or detection, we need fine-grained annotations, like this case. But because the images are so large, we cannot annotate a full image, right? So what we do is we extract patches of the larger image, which are small areas, and then we annotate the cells and the tissues. But yeah, this is how much we annotate. Of course, we can extract several patches from the same image to cover as much area as we can, but it's just infeasible to cover all the structures and all the image. It's really large, as I said. So it's infeasible to fully annotate. This is the second challenge. And the third one is the sources of variability across the images. We have multiple organs in our body, like here at the bottom, 3 examples, and they have wildly different structures. So it's hard to generalize. Also in this domain, we have stainings. Stainings are the colors or the chemicals that doctors use so that they can observe the biological components. And they can be different to enhance different structures in the data. There is a variability in relation to scanner, to the populations, etc. Okay, so we have three large challenges. Images are large. It's impossible to annotate the whole image because we do low-level vision tasks. And there are many sources of variability, which pose challenges to generalization. On the other hand, this also gives us a lot of research opportunities. Right? So let me introduce some. And this is how we are tackling some of these challenges. These are some examples. We do more than this. We tackle these challenges by efficient data annotation and by learning from unlabeled data through self-supervised learning. I want to say, though, that the method is, of course, very important. The architectures, the neural networks, but how we handle the data is really the key for success. So let's look first at how we deal with efficient data annotation. As I mentioned, we have many different types of images and organs. So when we start annotating, we have these cold start settings, which means that we don't have any annotated data in the beginning. However, we want to pick meaningful data since the first batch, because if we do this, our models will be as best as possible since the beginning. But as I said, these images are large and contain multiple structures, and some of these regions are really irrelevant, like these ones here. On top of this, many of these problems have class imbalance. There are cells that are way more common than others, or tissues that are way more common than others, although the rare ones are really important for us. So we could do random sampling of patches in the image, but it's somewhat unsatisfying, right? Because it wouldn't address some of these concerns. So what we do is sampling based on clustering. We start by extracting the patches from the whole images. We project these patches into an embedding space using a pre-trained neural network. And then we cluster these embeddings using k-means clustering in some predefined set of clusters, and then we can sample from the meaningful ones. To make this more clear, let's say that we have this HER2 data, and we run clustering in this way, and we can see that cluster A has a lot of these brown cells. And these brown cells, they are significant because this means that these cells can react well to this kind of treatment. So we need to sample from these cells so we can detect them well, right? We can sample more from here. On the other hand, this cluster D, we can see a lot of white regions or uninteresting regions, right? So, and they are quite common, so we can decide to sample less from these. And when we do this, what we can see here is the amount of data after annotation of each class on the left from cell detection cases, and we can see compared with random sampling that we significantly increase the amount of each of these cells. These are the classes of cells, and these are the positive cells that I was mentioning before. So we went from less than 1% to almost 10% in some of the cases. Similar for tissue segmentation, although smaller, but for example in this CIS case, which is super rare, we managed to get double the amount of data, and this makes a difference in the results. Okay, this was about how we select data in the beginning, but then we have another problem of how we efficiently or quickly or consistently annotate this data. And we do this through AI-assisted annotation, which means that we have an AI model that will support the annotators, the experts that are doing the job. Yeah, and annotation in pathology is really difficult. It's time-consuming because there are so many cells, and the tissues and the area that we annotate is large. It requires experts because regular people cannot do this. We need the pathologists doing this. The problem is, even pathologists, they disagree quite a lot between them. And unfortunately, as we know, deep learning requires large amounts of annotated data. So the performance increase here in this paper, at least, linearly with the logarithm, in the logarithmic scale. And of course, annotation cost is a big issue, especially when we are considering that we have experts. So we need AI-assisted annotation. And we published this paper this year in CVPR that deals with interactive tiny object detection, like cells, that can have multiple classes, okay? So this works like this. In the beginning, the annotator starts by giving a hint to the network, which is an XY coordinate plus the class, and the network receives this hint and the image, and then proposes some detections here. If the annotator is not satisfied, he can put more points in other objects here and feed these again to the network. And the network can refine this annotation. It's a loop, right? Until the annotator is satisfied. And to do this, we propose two modules that can be attached to any existing object detection architecture, like faster RCNN. One is late fusion model. The other is the class-wise collated correlation module, C3. And then we also have a user input enforcing loss. So this late fusion model deals with local context. we provide to this module the hint of the annotator and the image, and then we pass through an encoder, and this encoder will learn the relationship between the local hints and the image and the object, and then we concatenate this to the feature maps. The C3 model, on the other hand, allows us to get some kind of global context. Imagine the scenario where the annotator puts a point in the top left of the image in an object, and there are other similar objects in the image. We would like this hint to be propagated to the image so that we detect those objects too, those objects. What we do here is, given the feature maps and the hints, we collapse the feature maps into a kernel that is basically a template of that object in that location that the annotator gave the hint. And then we can just correlate all across the feature maps, and this will fire when there are similar objects. So it can help the network to learn features given the hint of the annotator. And in this way, propagate this hint to the other objects in the image. Finally, we also propose this user input enforcing loss, and this is more of a consistency loss. So when an annotator puts a hint in a cell and says this is a tumor cell, we don't want the network in the next step of the loop to say this is any other cell, because we know the true class of the cell. So what this does is that this enforces the network to obey the hint of the annotator. Okay, so we have these three components: the loss, the late fusion module, and the C3 module. And we test both on natural images in tiny data of small objects and our in-house cell detection dataset. And the results look like this. So in the x-axis, we can see the number of clicks of the annotators. This means the number of hints that they provide. On the y-axis, we can see the performance of the network. And the yellow one is the baseline, faster RCNN, without any hints. And the red one, the red graph, is the proposed method. And what we can see is that in both natural images and the cell images, the performance increases with the number of clicks. And this is really good, because this means that as the annotator puts more clicks, the more the proposed annotation is closer to the ground truth. So it improves the quality of the annotation. And here, what we can see on the left is that the time of annotation significantly decreases compared with fully manual annotation. And here, on the rightmost box plot, the lower is better. It's a measure of the notion of load of work. So lower is better. It means that the annotators felt that they much less load of work with the proposed method compared with the manual annotation. So this improves in the quality of annotations, making it faster and making it more reliable as well. This is a small demo. Let me just push forward. Yeah. So on the left, we can see the image that will be annotated. And on the right, it's the manual annotation, the ground truth. And the user can start by providing some hint, like there in the car. And the network will propose some objects. But the user is not satisfied. Some cars are not correctly detected, so they can provide another hint, and the network actually managed to fix some of the mistakes. Yeah, and then our user interface allows finally to clean up the image before submitting. Yeah. Okay, so this was about efficient data annotation. Now I would like to talk about how we are using unlabeled data through self-supervised learning. Let's just remind that this is how much data we annotate in an image, right? So we annotate these small patches, and all these images, they remain unlabeled, this area. And we have thousands of these images, actually. And recently, there is a lot of progress in self-supervised learning in computer vision that can enhance the performance by pre-training these networks in large amounts of unlabeled data. But there are two conditions for these methods to typically work. They require lots of data and compute power. And we actually have both at Lunit. So this is a comparison of our data set, including many organs and stainings, with the computer vision ones. So if we merge everything together, all the organs, stainings, kind of images, and different sizes of the patches, we have around 136 million patches unlabeled. In the computer vision domain, people can use ImageNet 21K, which has 12 million images, or JFT, which is a closed data set by Google with 300 million images. But look at this, the image size is much smaller than the ones that we have, so I claim that we do have a lot of images. And for these experiments, we tried to use Barlow twins for the results I'm showing today. Barlow twins is not proposed by us, it's from a state-of-the-art method in the literature. And it works like this. We have an input image, and then we transform this image twice. For example, the image can be rotated, or the brightness of the image can be changed. These two transformations are passed through similar encoders. And then at the end, we have some embeddings. Okay? And then the Barlow twins propose a loss function that computes the cross-correlation matrix between the embeddings and tries to make it match a diagonal matrix. On one hand, to decrease correlation between the features after transformations, and on the second hand, to make more meaningful features. And we use this to pre-train a backbone, and we use this backbone for an object detection network or a segmentation network, and then we fine-tune on the downstream task. For example, cell detection or tissue segmentation. And when we do this for lung cell detection in PDL1 data, what we can see here is that, well, when we train from scratch, we get this performance. But if we train from a pre-trained network on ImageNet, the performance increases, but it increases further if we use self-supervised learning on our own unlabeled data. And this is true for both validation and the test set. This is also true for the tissue segmentation task in H&E images that contain up to 16 organs, okay, many different organs. It allowed our network to perform better when compared with a network that is pre-trained on ImageNet. Yeah, so to conclude for today, we do have a huge amount of data from different sources in pathology. And we saw three main challenges and how we are tackling these challenges through efficient data annotation and by utilizing unlabeled data by self-supervised learning. And I want to conclude by saying that in the real world, to get world-class performance, the model is important. It's really important. But tackling the data and the domain properly is really the key for pushing us to the next level. And in recognition of this, at the Oncology AI Research Group, we have both model-centric AI teams and data-centric AI teams that collaborate and allows for pursuing these two directions. Okay. So final words, at Lunit we are really focused on our mission, and we will improve the survival of cancer patients. And we have everything we need. Very talented and passionate researchers, excellent medical and product teams that guide us in the products that we want to do to have large impact. And we have large-scale data and compute resources in the cloud. So finally, I want to thank my team members in the Oncology AI Research Group. Today's presentation is a showcase of their work, actually. And thank you for listening.